Section 22.19 Metallocenes. When there are 4n plus 2 conjugated pi electrons in a ring structure, it's aromatic. For example, benzene, pyridine. When there are 4n conjugated pi electrons in a ring structure, it's anti-aromatic. For example, cyclobutadiene, cyclooctatetraene. In this case, the ring often becomes non-conjugated, such as in cyclobutadiene. In this structure, you have 2 double bonds and 2 single bonds. Or it may become non-planar just to eliminate the anti-aromaticity. For example, this cyclooctatetraene structure is non-planar. There's no conjugation in this cyclobutadiene or in this cyclooctatetraene. There's no conjugation. The reason I talk about this is because I want to make sure that you understand this C5H5 is an anionic ring structure and it's aromatic. In this transition metal complex, this iron is actually iron 2+. And you have one negative charge on each of these 2 ring structures. So it's C5H5 minus. Really, it's CH, double bond, CH, single bond, CH, double bond, CH, and then CH minus. And then you form a ring structure. The CH minus has a p orbital occupied by 2 electrons. And then you have 2 double bonds. So that's 4 more p electrons. In total, we have 2 plus 4, 6 p electrons, forming this conjugation on this 5-membered ring. So this is aromatic. The cyclopentadienyl anion is aromatic. So how do we make this? It's pretty simple. Potassium hydroxide, this is neutral cyclopentadiene with 2 double bonds and a CH2 group. And then over here, this is just to provide this iron 2 to form this metallocene of iron. Subsection B, bonding in bis eta 5 cyclopentadienyl transition metal complexes. I'm going to show you an example here. There are 2 C5H5 minus right here. And then this is our transition metal, very likely 2+, because this cyclopentadiene will need 1 additional electron from the metal. And then there are 2 rings. So this metal will have to give away 2 electrons. And this metal becomes 2+, and then we have 1 minus charge on each of these 2 5-membered rings. This MO diagram is really complicated, but I want to remind you this structure is highly symmetric. It belongs to the D5H point group. So over here you can review group theory. There's a C5 principal axis, right? And there are 5 C2 axis perpendicular to the C5. All these 5 C2s pass through this transition metal center. And also, I think you can easily find this sigma H that's perpendicular to the principal axis, right? And also, you can rotate maybe the top ring structure 180 degrees, and it becomes D5D point group. Okay, let's get back to this D5H point group. And let's look at the metal on the right-hand side. Let's look at the 2 ring structures on the left-hand side. In this D5H environment, we have the 5 d orbitals split into 3 different energy levels. dz squared, dx squared minus y squared, dxy, and then dyz dzx. These 2 are doubly degenerate. These 2 are also doubly degenerate. This is just the 4s orbital in iron. These 3 are just the 4p orbital. 4p orbitals in iron. So this 4p orbitals are empty. This 4s orbital is also empty. And over here, if we're talking about iron 2+, I think we have 6 d electrons coming from this iron 2. Now let's look at this one. Let's look at this C5H5 minus. You have A1 prime, that's completely symmetric. I think this corresponds to Over here, you can imagine the 5 lobes pointing up from the bottom ring. And also there are 5 lobes pointing down from the top ring. And all these 10 lobes are pointing toward the center metal. Okay, again, I need you to picture 5 p orbitals on the bottom ring and the 5 p orbitals on the top ring. Okay, the bottom 5 lobes from the top ring and the top 5 lobes on the bottom ring have the same sign, same phase. Okay, and then it can interact with dz squared over here, right? Dz squared. This is also completely symmetric in this D5H point group. So this A1 prime interacts with this A1 prime. A2 double prime. So again, you have 5 p orbitals on top, 5 p orbitals on the bottom. But over here, you can imagine this 5 p orbitals with 5 lobes pointing towards the metal. They have the same sign. And on the bottom ring, you also have 5 p orbitals, 5 lobes pointing toward this metal. But the top ring has 5 lobes with a different sign, or with the same sign. The bottom ring also have 5 lobes with the same sign. But the 5 lobes from the bottom and the 5 lobes from the top, they have different signs. Okay, they have different signs. So in this case, this A2 double prime will interact with, I need to find A2 double prime, the green line all the way up there, over here. Oh, p orbitals, pz orbitals. If you look at the pz orbital, it's centered on the metal. So you imagine we have 2 lobes. We have plus lobe pointing to the top ring, minus lobe pointing to the bottom ring. And the top positive lobe interact with the 5 positive lobes of the 5 p orbitals of the top ring. Okay? And again, we're talking about the 4 p orbital centered on the metal, 4 p z orbital. So there's a negative lobe in this 4 p z orbital. The negative lobe interacts with the 5 negative lobes from the bottom ring. So that's how this pz interact with this A2 double prime. Of course, there are just many other interactions. If you are interested, I'll let you look at those. You just need to make sure that the symmetry of the d orbitals, 4s orbital and 4p orbitals, match with the orbitals from this 2 C5 H5 minus rings. Okay, 2 orbitals can interact with each other only if their symmetries match. And the interaction is strong if the 2 orbitals have similar energy. The interaction is weak if the 2 orbitals have quite different symmetry. All right? So I think there's going to be some mismatch. For example, the orbitals in the middle. So they are weakly bonding orbitals or weakly anti-bonding orbitals. So they are more like non-bonding orbitals. So that means you can put electrons in these orbitals, and you can also choose to leave these orbitals empty. All right. So either way, there's not much impact on the total energy of the system. So that's why the violations of the 18 electron rules are pretty common in those metallocene structures. Subsection C, fluxional behavior of metallocenes. Now let's look at this 2 metallocenes. You may wonder, how is this possible? Are you showing me a anti-aromatic planar cyclooctet tetraene? 1, 2, 3, 4. Yes. If you have a planar cyclooctet tetraene structure, it's anti-aromatic with 8 pi electrons. Well, however, it's highly possible for this transition metal to either get 2 electrons from the ring or to donate 2 electrons to the ring. And then this ring structure will have 6 pi electrons or 10 pi electrons. And this structure becomes aromatic and, of course, planar. So it can be planar as long as this cyclooctatetraene gets 2 electrons or gives away 2 electrons. But on top of that, even if this becomes aromatic and planar, this transition metal may not interact with all those pi electrons or all those 8 points of attachment. So in this case, this is eta 1, 2, 3, 4. This is eta 4, not eta 8. It's eta 4. So again, when you have this kind of conjugated network, you may have the Greek letter eta 8 or 6 or 4 or even 2. In this case, you're looking at eta 4, and also this ruthenium may be bonded to not necessarily this 4 carbon atom. It can kind of move around. Now in this structure, it's bonded to 1, 2, 3, 4. This 4 atoms. So it kind of shifted just 1 carbon atom, and it can keep shifting within this ring structure. Subsection D, bent metallocene complexes. Well, these 2 rings do not have to be parallel to each other, so you can have a metal here bonded to these 2 rings, and then you can have some lobes here. For example, let's look at this structure. This is titanium 4+ with 4+ charges. Okay, this titanium has now 0 d electrons. So this titanium gives away 1 electron to this chloride. This becomes chlorine minus. And these 2 are carbon 5, hydrogen 5 minus. All right, so minus, 4+. Now we have 2 sigma bonding electrons here, 2 here, 6 from this ring, 6 from this ring. So 6 plus 6 plus 2 plus 2. You have a 18 electron system. Over here we have a different transition metal. Tantalum bonded to 3 chlorine, and then bonded to this 2 C5H5 minus rings. This is also D0 because it's tantalum 5+. This is tantalum 5+. You have chlorine minus, and then this is cyclopentadienyl Ni, but it's surrounded by 18 electrons. 2, 2, 2, 6, 6, a total of 18. So in this cases, we have bent structures. Now let me show you another example. You may see this example in the lab menu of Chemistry 382 lab at Central Washington University. You're going to look at this ring structure here. This contains 5 sulfur atoms and titanium. This titanium is also bonded to 2 eta 5 cyclopentadienyl Ni. So we have a negative charge here. Okay, a negative charge here. A negative charge on this sulfur, a negative charge on this sulfur. These 3 are sulfur 0, these 3 are neutral. So this is again titanium 4+ with a negative charge here, a negative charge here, a negative charge here, a negative charge here. So overall this complex is neutral. And this titanium is surrounded by how many valence electrons? 2, 2, 6, 6. A total of 16 electrons. So in this reaction, it's pretty simple. When you have a 6-member ring structure, this is shear conformation, and you can have axial position, you can have equatorial position. So I think it's possible to observe the conversion between the axial position and equatorial position. Okay, this 2 rings, one may occupy the axial position, the other occupy the equatorial position. That's, I think, distinguishable in the NMR spectrum as long as the flipping of the ring is slow enough.